particular course, we will follow a methodology similar to what we did for vehicle dynamics. That is, I have shared the links of all the class videos. So please watch the videos and come to each class. In each class, we will discuss the corresponding video. And then like we will have questions, answers, interactions, and so on. And as the course progresses, we will also have some projects which will be, the project statements will be given. And Sai Abhinav, who is the TA for this course, will also help you in completing those projects. But that will come later, where we will have some hopefully real life case studies where we apply the theory concepts that we learn in this course to real life automotive case studies. So that's something which I feel will be interesting and relevant. So we will do that as the course progresses. So this course ID is ED533D0W, and it's called Control of Automotive Systems, right? So the overall objective is for us to motor course, and this course builds on two important things, like vehicle dynamics, which all of us have already learned, and a control theory, which we are going to learn in this particular course. And then like we will combine both of them, and then like see how do we design control systems for automotive applications. Okay, and some part of the fundamental part of this control theory is something which you and I have already learned through our vehicle dynamics course, because if you remember in the vehicle dynamics course, in the first part, we learned about dynamic systems, right, in general, where we talked about stability, performance, and so on, right? I hope that you will have a chance to recap those concepts as we go along this particular course. We are going to build upon those. Okay, so we'll also quickly recap those ideas as we go along in this particular discussion. Okay. Sorry. So the grading policy of this course will be that 50% of the course will be primarily based on homework and projects. So 25% each for the midterm exam and 20 for the final exam, respectively. Okay. So we will decide on the dates for the midterm exam as we progress in a couple of weeks, so that you and I can figure out when we'll have the midterm exam, and then the final exam towards the end of the semester. That's what we will do. Okay, so that's going to be the grading policy, and I have given you all the videos and also this PDF file notes, right, already to you. Right, I had recorded it during a few years ago. So I think now it's proving to be useful, because we can use this flipped classroom learning for better learning and discussion, in my opinion. Right? Okay. So that is the grading policy. Any questions on the grading policy? All right. Okay. So we will take this as the grading policy, and then we'll proceed. So we will quickly recap what we did in vehicle dynamics, and then we'll start building with that. So if we recollect when we started vehicle dynamics, right? So you and I would have learned broadly about dynamic systems, right? On their characterization. So by the word system, we are referring to an entity to which we provide an input U of t, and we obtain an output y of t from it, right? So that's for a system for us. And the word dynamic is used to indicate that that variables associated with the system are all functions of time, right? Time is the independent variable. So we write y of t equals s time s of u of t. Okay, so where s is the mapping between the input and the output, which is the mathematical model of the system. So in vehicle dynamics, you and I would have learned to derive this mathematical model for various applications, right? Let it be drive or braking or cornering or ride dynamics, where we looked at the suspension model and so on, right? So where we looked at how the system output or response is related to the system input. Now, when we look at the problem of control, we are doing a reverse problem. That is, the broad question, philosophical question that we will be asking ourselves is that, can I now invert this mapping S such that I can figure out what is the input that is required to get a certain desired output Y of t? Okay. So what do we mean by that? Let's say, even if we are looking at, some autonomous vehicle, right? So where we want the vehicle to follow a certain trajectory, then using the dynamic bicycle model, you and I would have learned in vehicle dynamics how the heading and the orientation or the path of the vehicle changes when we give a steering input. But now, let's say I want to go on a particular path. The question arises, what steering should we give, right? So if we look at the bicycle model that you and I learned, so the steering input delta t, right, was related to the orientation angle psi t, the side slip angle beta t, and so on, right? Now, in control, right, we want a desired orientation. Okay, there is something which is desired. Now the question is, what should be the corresponding steering angle, right? That will get there. Okay, so that is what we will be looking at in this overall course, right? So we learn the generic methods. We will then apply it to automotive applications. Okay, so the class of systems that we will consider remain the same. So you remember the class of single input, single output, linear time invariant, causal, dynamic systems, right? So that remains the same, as what we did in vehicle dynamics, right? So single input, single output, the meaning is obvious. Linear, we know the definition of linearity, right? So we give two separate inputs, U1 and U2. We get two outputs, Y1 and Y2. We give C1 U1 plus C2 U2. We get C1 Y1 plus C2 Y2, right? So that's the definition of linearity. So do you recall the definition of time invariance?